Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. So as we approach the end of Algebraic Calculus 1, we are kind of looking at applied aspects of the course and connecting with important computational problems. And in particular, we want to say a little bit about the log tables that classically have been so important in the history of computation. And these were associated with gentlemen Napier, Burgi, and Briggs. And although our approach is, in fact, much more general and perhaps somewhat more sophisticated than what they were doing, there's actually quite a lot of parallels when you actually get down to nuts and bolts of things. And the way we're going to approach it, we're going to be able to recover the kinds of thinking that, that led to their tables, but we're also going to see that the same kind of reasoning can also be applied to the other geometries to reveal interesting relationships that we'll explore in Algebraic Calculus 2. Okay, so I've been trying to convince you of this important global view towards the log and the exp relations. I want you to think much more generally than in the usual fashion about what's really going on here. And so we have these three geometries, the familiar blue geometry, the red relativistic geometry, and the green relativistic geometry. And here are the unit circles in all three cases. And each of these comes together not just with geometry, but also with algebra, because there's a complex number system behind each one of these. Okay, so the fundamental relation that we want to explore is the relationship between a point on this unit circle, say Z, and the corresponding signed area, or approximate signed area, S. That's formed by taking a sector of the curve from the fixed point 1 to the point Z. So we're kind of going along the curve in a certain direction. It's like a curve vector, and that gives us this sector, and then the approximate signed area of that is S, and that's somehow connected to the point Z. Over here, the situation there is the point 1, and there's a point Z on the curve, and we're talking about this signed area here. And over here, the point 1 is here, and Z is somewhere perhaps there, and we're talking about this signed area here, which in this case will have the opposite orientation to these ones. Now, to make this proceed a little bit more smoothly, it helps if we sort of restrict ourselves. So to avoid topological difficulties as much as we can, we're going to sort of snip the unit circle right at this point here. So we snip that. So we're not allowed to go across this point. Okay, so we'll stick to Z's in the upper half here, emanating from 1, or in this direction emanating again from 1. And over here, we just ignore this other branch and restrict values of Z to this branch. And similarly over here, we ignore the branch down here and just restrict values of Z to there. So in all three cases, we get a relationship between the S and the Z. We say that S is the log of Z, but it's a capital L log. It's like a bigger log than the usual one. And correspondingly, or inversely, Z is exp of S. Again, with a capital, this is a bigger kind of function than the usual exp. Now, the ordinary or more familiar garden day variety log and exp are actually associated with taking these two things and just restricting to the green picture. Okay? But what I'm trying to suggest is that the basic principle actually applies uniformly across all three pictures and gives us a more general framework to see not just the log and exp functions, but actually also the cosine, the sine, the cosh, the sinh functions, and so on. But the full development of that, especially with a little bit more rigor than the approximate approach that we've been taking now, we'll have to wait to Algebraic Calculus 2, where we're going to have to develop some more sophisticated algebraic technology to be able to say the kinds of things that we want to say exactly, more carefully. So if we have a computational frame of mind, we want to know how do we actually calculate these logs and exponentials, even if we know that we're only talking about an approximate setting. So let's have a look at the green geometry. And there's our nice standard hyperbola there. And we're going to put coordinates on things so that we can compute things with respect to a particular coordinate system. And a natural place to start is with the coordinates that we've already introduced for the standard hyperbola, where we think of the curve as being 1 plus alpha, comma, 1 over 1 plus alpha. So a point z there might be g of t, where g of t is 1 plus t, comma, 1 over 1 plus t. In the case when t equals 0, we're at the point that we're calling 1. It's the point with actual coordinates 1, 1. Now we know that when we're talking about a curve like this, it's not a polynomially parameterized curve because there's a rational function there, but nevertheless the same principles at least roughly apply. And the first order of business is to calculate the area differential, p dq minus q dp. And it's not hard to do. In that case, the area differential is minus 2 over 1 plus alpha. So that means if we're integrating, even approximately, the curve, say from t equals 0 to a value of t, s from 0 to t of gamma is, by the fundamental theorem, which we're going to happily extend to this situation, at least roughly, will be 1/2 of the Faulhaber integral from 0 to t of this area differential d of gamma. That's our fundamental theorem. Now there's a 2 here, which will cancel with that 2. There's a minus sign that comes out, and we're left with the Faulhaber integral from 0 to t of 1 over 1 plus alpha. Now, this is not something that we have defined in terms of the Faulhaber integral. We do not know how to do this. This is not a Laurent polynumber, okay? But what we can do is employ the kinds of reasoning that we've already seen, is to approximate this thing at some level with some polynumbers and then think about their remainders. So we can write 1 over 1 plus alpha as 1 minus alpha plus alpha squared minus alpha cubed. It's like a little geometric series. And then the extra thing that we have to add to make things equal is alpha to the 4th over 1 plus alpha. If we go up one term, we get 1 minus alpha plus alpha squared minus alpha cubed plus alpha to the 4th, and then we have to subtract alpha to the 5th over 1 plus alpha. So these are just identities of rational or quotient polynumbers. So now if we look at these things and say, all right, so suppose that we're thinking about alpha as being some number t, and suppose that t is positive, so that it's in this region here. Then what can we say about these things? Well, this quantity here will be t to the 4th over 1 plus t. That's going to be a positive quantity. And similarly, this is going to be a positive quantity. And so that means that 1 over 1 plus t is this thing plus something positive. So we can say that this with 1 over 1 plus t is going to be greater than or equal to this quantity when we replace alpha with t. 1 minus t plus t squared minus t cubed. In fact, we know exactly what the difference here is. The difference is this quantity here when alpha is replaced with t. And similarly, on the other side, we can say that this quantity here, 1 over 1 plus t, is less than or equal to what we get by replacing the alpha with t here. 1 minus t plus t squared minus t cubed plus t to the 4th. And the difference here is exactly this quantity here. So we're in a pleasant situation. We don't know how to integrate 1 over 1 plus t in the Faulhaber sense. But we've sandwiched this quantity between two polynumbers that are relatively easy to integrate. Okay? So that's a basic kind of idea, to try to get at some at least approximate region where we have some scope for saying, okay, the integral of this thing is going to be somewhere in this region. Okay, so now we're going to make the same kind of assumptions that we've made already several times before. We're going to assume that the Faulhaber integration process respects inequalities. So that if we take the inequality that we've just looked at and we apply the Faulhaber integral from 0 to t of everything, then the inequalities are maintained. So for t greater than or equal to 0, we have that the integral from 0 to t of this quantity is less than or equal to the integral from 0 to t of 1 over 1 plus alpha, whatever that should be, which is less than or equal to the integral from 0 to t of this quantity. Now, happily, these things are easily integrated. So from 0 to t, we get t minus t squared over 2 plus t cubed over 3 minus t to the fourth over 4. This thing here is the same. And over here, the same kind of thing, but with an additional t to the fifth over 5 term. And there's nothing particularly special about going up to level 4 here. We could have gone up to general even power. The same kind of thing would have happened. We could have gone up to t to the 6th and had a t to the 7th over here. The argument would be exactly the same. So here is the general form for the inequality that I've written a special case of here. The sum from k equals 1 to 2n of minus 1 to the k plus 1, so we're alternating plus and minus, t to the k over k. Less than or equal to the signed less than or equal to the Faulhaber integral from 0 to t of 1 over 1 plus alpha, less than or equal to sum from k equals 1 to 2n plus 1 now of the same quantity, minus 1 to the k plus 1 times t to the k over k. So the difference between the right-hand side here and the left-hand side, just like here, is this last term that appears. So that's, in general, t to the 2n plus 1 over 2n plus 1. So we have our integral sandwiched between two things, and we know what the difference between the lower bound and the upper bound is. It's exactly this expression here. Now, what happens as n gets large here? As n gets large? Well, this thing does not necessarily get small, because if t is bigger than 1, like say t is 3 or something, then we're getting 3 to the 2n plus 1. That's going to get big as n gets big. However, if t is in the range 0 to 1, then these powers will always be between 0 and 1 also. And then the fact that the denominator is getting big means that this whole quantity here, which is the difference between the left and right-hand sides, is going to get smaller and smaller and smaller. So it means we're effectively sandwiching what we're interested in between two things that we know exactly what they are. So notice, however, that this argument really requires this restriction on the values of t for which this works. Okay, so if we go back to our picture, it's not that you can take any old z and expect to get a value for the log this way. Only if t is small, in other words, close to 0, between 0 and 1. Okay, so that's an important point. So we can summarize what we've done, call it Mercator's formula. We've got an expression for the approximate signed area, S here, formed from the curve and a point 1 and a point z on it, where z is 1 plus t, comma 1 over 1 plus t. So for t positive, the approximate signed area, S, which is signed area from 0 to t of gamma, satisfies for n equals 1, 2, 3, etc., the following inequality. That minus s, we have to put minus here because this integral, the way we've got it here, is actually negative. So if we want something positive, we want it to put a minus sign there. And that's going to be then sandwiched between the sum from k equals 1 to 2n of minus 1 to the k plus 1 t to the k over k, and the same kind of sum, k equals 1 to 2n plus 1 minus 1 to the k plus 1 t to the k over k. Now, note this inequality, this sandwiching, is valid even for bigger t. It's just that the difference between the right-hand side and the left-hand side happens to be small only when t is in this range between 0 and 1. Okay, so when t is close to 0, so relatively close to 0, and z is then pretty close to this point 1, then this bound becomes rather effective. It allows us to actually compute s rather effectively. Of course, we never get at s exactly. That's just an aspect of the way the world is, okay? But we get bounds which can be made quite tight. So that's very useful computationally. Now, the very first log tables were created by the Scotsman Napier and the Swiss instrument maker Burgi around the beginning of the 17th century. So this was before calculus, really. And we're going to be following their basic orientation here, the idea will be to look at the correspondence between a geometric series, like powers of a particular value of z, and the corresponding sort of indices that in some sense correspond to the signed areas. Okay, so they did not think in terms of the curve x, y equals 1 or in terms of signed areas. They rather just thought about the relationship between essentially an arithmetical sequence and a geometrical sequence, but we'll see that it's very much the same. So the starting point for us is to evaluate a log for a particular value of z. And we're going to choose a value of z which is very close to 1, because our estimates are very good when z is close to 1. So in particular, we're going to try to compute log of z, which is s, when z equals g of 0.01. In other words, we're going to set t equal to 1 over 100. So there is the corresponding point z, 1 plus t and 1 over 1 plus t. So 1.01 and 1 over 1.01. That's actually g of 0.01. Sorry. There we go. Okay, so what do we know about this signed area S here? Well, we've seen this bound. This is the same kind of bound that we've already established. Minus S is between this expression and this expression. And t is happily 1 over 100. That means that the difference between the left-hand side and the right-hand side is exactly this quantity here when t is 1 over 100. That's 10 to the minus 2. So there's a t to the 5 here. That's going to be 10 to the minus 10, and then we divide by 5. That is a very small quantity. Okay, it's a very small quantity because the t value that we're using is so small. In fact, the left-hand side here turns out to be exactly this fraction here. 11940397 over 12 with 1, 2, 3, 4, 5, 6, 7, 8 zeros. And on the right-hand side, 373137407 over 37500000000. Now, it doesn't take too long when you're working in this area to start to appreciate how awkward fractions are and how much sense Simon Stebbins' orientation was saying, forget about fractions, do your calculations with decimals instead, even if that involves truncating them or rounding them. So that's almost always the more effective, actual applied computational approach to calculation type questions. So we calculate at least an approximate decimal expression here, and we get on the left-hand side 0.009950330833 less than or equal to minus s, which is less than or equal to 0.009950330854. Now, this decimal is not exactly equal to that fraction, okay, but there's something else we've truncated here. But we see that we have agreement with these decimals up to the place that I've marked here. So the 3 there, the 5 there, that's the first place where there's some disagreement. That's really solidifying our understanding that yes, this is a very good approximation. We've sandwiched minus s between these two things which are very close to each other because they only differ in the 3, 6, 9, 10, in the 11th decimal place. All right, so now we can start making a log or exp table very much in the same way that Burgi and Napier did. Very much in the same way. So what we do is we take that single computation that we started with, and that was the log of, well, the complex number whose x-coordinate was 1.01, that's the 1 in 100th, and whose y-coordinate, to 6 decimal places, is 0.990099. That's 1 over 1.01. Okay, and there is that value of s that we've computed where I've truncated to 6 decimal places. So I'm truncating to 6 decimal places in terms of representing things, but to actually make the calculations here, it's better to use more decimal digits. so that rounding errors, truncation errors, don't creep into the story for as long as possible. Okay, so you make the calculations with bigger decimals, but you exhibit smaller ones because maybe you don't have so much room. Okay, so this is what you end up getting. So you take, here is the value of s, and here are just going to be multiples of s. So that's s, that's going to be actually minus s. And there's 2 times that, and there's 3 times that, and there's 4 times that, and so on. And over here what we do is we take the powers of z. So if this is representing the point z on our curve, then this next line represents the point z squared, obtained by squaring the x-coordinate and squaring the y-coordinate. And again, I'm always truncating to 6 decimal places. I'm actually truncating, not rounding, okay? That's a point that will become clear in our next course, but I'll let you know now. And there's the cube of 1.01. There's the 4th power. Actually, making these powers is actually not so hard because at each stage you just multiply by 1.01. Right? So to get the next one, you would take this thing here, move it over twice, and then add. That's relatively painless. Okay, so we could keep going, and then there's some intermediate steps, and I've just sort of fast forward to the value where the s has gotten up to the value close to 1. So here is 0.995 something, and here is 1.004. So we're just straddling 1, and the corresponding x and y coordinates are, well, here roughly around 2.704 or 2731, and over here 0.369, 0.366, something like that. Now, in Napier's or Burgi's point of view, they would not have thought in terms of a point on the curve. They would rather just have restricted, say, to the x values. And so here are some values, and here are some other values, and going from these values to these values is the exp function, and going from these values to these values is the log function, in a very classical kind of setting. Okay, so the original tables of Napier and Burgi would only have sort of these 2 quantities, but again, I want to give you this bigger picture. I want you to think in terms of actually a point on the curve. That's sort of what's really going on. So to summarize what we've been doing, we've been looking at the relationship between signed area S and a corresponding point Z on the curve. And Z is, say, 1 plus t over 1 plus t. That's our sort of standard coordinatization of, or parameterization of the curve. But we could also, if we wanted to, express the point Z in terms of the x and y coordinates. Okay. So the relationship is that S is the capital log of Z, and Z is the capital X of S. Now, to connect this more directly with the traditional little l log and the little e exp, we're going to do the following. We just have a look at the relationship between S and just this x coordinate. So we ignore the y coordinate, take this point on the curve and just look at its x coordinate. And because our signed area happens to be oriented this way, because we're conscious of orientation, so this happens to have a negative orientation when z is in this position here, we're going to say that minus s is log of x. Okay, so we want to relate the value of s, actually the value of minus s, with the number that's appearing here in the x coordinate. We can say that the log of this number is minus s. That's exactly the relationship that I pointed out between the first and the second of the columns that we were just looking at. And correspondingly, going the other way around, x is exp of minus s. Okay, and then we have the familiar pictures. If we just graph the values, always approximate, between x, say, and log x. So we look at y equals log x, everything with quotes, or y equals exp of x, also with quotes. Then we get functions which are traditionally sort of graphed something like this, and the inverse relation like this. And they satisfy the usual familiar properties. Log of AB is log of A plus log of B, and exp of A plus B is exp of A times exp of B. These are the crucial defining properties of these two functions. Okay. So, but I want you to think about these things as being sort of specializations of this rather more general, lofty, large-scale view of what's going on, just the relationship between a point on a curve and a corresponding signed area. Okay, so we started to make this log table by taking that particular very small value of s and then looking at multiples of it and corresponding powers of the associated z. So we could carry on doing that and spend actually quite a long time, because we have to take powers and you have to do everything to quite a few decimal places to get something accurate. And then we get this big table with hundreds or thousands of entries. And that's exactly the kind of thing that Napier and Burgi did. But it turns out that Briggs, who was a professor, either at Cambridge or Oxford, was very enthusiastic about Napier's original work and went up and visited Napier and started having some very useful discussions with him. And the two of them started to realize that there was a kind of a weakness in the Napier's original formulation of things that made it less effective computationally than it could be. And so we want to talk about that. It really has a lot to do with the particular value when s is equal to 1 or minus 1. So when I showed you the table originally, I gave you two values of when the signed area is approximately 1 or minus 1. Okay? We saw that it was roughly when x was something like 2.7 something and y was something like 0.367. In fact, this is sort of like pretty close to the average of the two values that I showed you. So it's right at this stage here, right at that point there, okay, where this signed area that we've been accumulating ends up having the total value of 1 or minus 1 if you include orientation. And that's actually quite an important value. And so traditionally, in classical mathematics, we say that, okay, we're going to introduce a new irrational number, and that irrational number is e, and it represents what you get when you take this decimal expansion and you keep, introducing more and more accuracy into the story, and you do an infinite amount of approximation to get this infinite decimal. And you all know that, for me, that is just not a viable thing to do, so it doesn't really make sense to talk about that. So this quantity e, just like the quantity pi or any other irrational number, is only approximate. But nevertheless, this is approximately e, and this is approximately 1 over e. Okay, but Briggs and Napier came to the conclusion that it was more useful to have actually a very nice value where the total log is reaching the value 1. And nice for them meant that's related to our decimal number system, because that's where we do our computation with. We do computation with decimals, and so the number 10 plays an important role. And so if we can rearrange the log by sort of rescaling it, then we can arrange that the log of 10 is 1 rather than the log of e. Okay, so what that amounts to is this relatively simple formula. What we do is we introduce a new function called log sub 10. Log sub 10 of x is by definition log of x, what we've already defined, divided by log 10. Okay? So we take the log of 10. So you have to go 1, 2, 3, 4, 5, 6, out to 10, okay? And you have to take the log of all the signed area underneath the standard hyperbola from 1 to 10, okay? That's log 10. Now it takes some work to evaluate that. That's a nice little kind of series of exercises that we'll talk about in our course. So you have to do some work to get a log 10. It's not so easy because you can't just directly use the Mercator formula, because the Mercator formula doesn't work in this range. So you have to be a little bit more clever. But one way or the other, you can get log 10, and then you just divide the current values of log by this fixed value of log 10, and you get this new log function, log to the base 10 of x, let's say. And pleasantly, it's easy to check that it has the same crucial property with respect to multiplication, that log to the base 10 of the product AB is the sum of the log to the base 10 of A and the log to the base 10 of B. But now in addition, it has the beautiful property that log to the base 10 of a power of 10, say 10 to the n, is just n. So in particular, if n is 1, log to the base 10 of 10 equals 1. And that then is a log that has been carefully oriented to mesh with our decimal number computational system. And it's this step that really made the theory of logarithms a hugely powerful tool in the 17th century. And Napier died a few years after their conversation, and so it was left to Briggs to sort of redo Napier's tables. Napier had already spent many years making his tables. Now Briggs spent some more years making these modified tables where everything was to the base 10. And once that was done, well, then the 17th century had the most powerful computational tool. It was the 17th century equivalent of a calculator. It was really that powerful, and it just completely renovated computation, especially astronomical computations, and empowered people to do all kinds of computations that earlier would have been very onerous. All right, so when I was growing up, we actually used log tables. They were a very important computational device even then. Nowadays, of course, they're almost always superseded by calculators and computers. But still, it's, I think, very illuminating to understand, how these things operate, where they come from, and actually be able to function with them. So it's actually something that I want us to appreciate in the algebraic calculus. So here is a classical log₁ table. So after Briggs comes along and spends a lot of time sort of rethinking how to make this thing sort of computationally effective, then it's sort of rewritten. So it's the same kind of data, but we're kind of presenting it in a nicer way with this base 10 orientation. So we just have x and log to the base 10 of x. Okay, so this is like x, and this is the s value, or sort of minus s, but rescaled. Okay, so when x is 1, namely the x coordinate is 1, then the log is 0. When x is 1.01, we get 0.004321. So that's less than about less than half of what we had before, because we have to divide by the log 10. Okay, and then 1.02, 1.03, and so on. So you can imagine having hundreds of thousands of entries. In fact, this is not very fine. Actual serious log tables are finer than this. They go to 3 or 4 decimal places. Okay, so there's a lot more entries. Okay, so anyway, the table would carry on, and eventually the x value would get to 2. And then there would be, in this case, another 100, and then we get to 3, and then to 4, 5. So here are the values of log of 2. Log to the base 10 of 2 is 0.30103. Log to the base 10 of 3 is 0.47712. These things have nice relations. For example, the log to the base 10 of 2 plus the log to the base 10 of 5. If you add these two, you're going to get 1, because that's the basic law. So it turns out that actually if you sort of memorize just these sort of 10 or 9 values, you can actually calculate logs without too much work. So just with these integral values and a little bit of playing around with products and quotients means that lots of other numbers can be calculated reasonably easily. So if you were stranded on a desert island and you had to only take a little bit of information with you, taking these 9 or 10 values along would be quite a useful thing, actually. Okay. So this is the manifestation of our big log, big X picture. In the special case of the green geometry, we see that we connect directly with very historically important things. But of course, still the question remains, well, how does the story go with the blue and the red geometry? Well, then we end up doing something analogous, but we touch base with trigonometric tables, either circular or hyperbolic. And then there's relations between all these three pictures because the underlying geometry is really one and the same. And there's nice relationships between the conics and correspondingly nice relationships between the corresponding functions. But to make that all more accurate and sort of take it out of the level of approximation, which is what we've been talking about in the last a few videos, we really need to do some more work, and we're going to be doing that in the algebraic calculus too, along with many other things. So there's much to learn. I'm Norman Wildberger. Thanks for listening.